Hello everybody and welcome to this, my corner of the internet. I am SD Card and this is the final episode in my series on OCR GCSE Computing. Today we're going to be this episode I'm going to talk about programming, and so I'll try and keep this as short as possible, however it is a fairly long chapter. Okay, so first off, flowcharts. Okay, so when playing code, you need to have an easy and simple way to plan out your code in order to see it and go through it and make sure that you've got everything that you want and need. So, and there are two main ways that you can do this. There is flowcharts, which I'm going to go through first, and then there's pseudocode, which is a lot simpler, and I don't think I've got anything set up ready for demonstrating it because it's that easy. So basics of a flowchart is that it uses symbols and pictures in order to show different processes the computer can do. So the four main ones that you need to know for GCSE are that a oval or ellipse means start or finish, so they appear at either ends of a program. That a rectangle or square is a simple process like adding, subtracting, or accessing a file. And then you've got a parallelogram, which represents either inputting or outputting data. And then finally you have a diamond, which means to make a decision, and that will have it'll have a minimum of two outputs. It'll either have a yes or a no, or maybe a selection of different inputs. So it's like maybe with maybe each arrow coming out of it represents a different key on the keyboard, and all of these are connected using arrows, and the arrows point in the direction that the code will run. So in this very simple example here, it goes start to finish, then a process, then input and output, or an output, and then to a decision with the output. If the output is no or false, it'll go back to the input output stage, and then if it is yes, it finishes the program. So I actually have a simple flow diagram set up here to show you. So here I have this is a website called draw.io, and I set up a very basic flow diagram that I'm just going to talk through quickly. So first you have the start, so you start the program there. Then it tells you to input num1. So basically num1 is the name of a variable, and we'll cover the variable later, that you're going to store your input in. Okay, and then you have input num2, which tells it which basically means you have to input a second number, and again that is then stored in num2. Then you have a process, which is basically storing the result of num1 plus num2 into a third variable result. Then we have a decision with a very simple question: is the result greater than 10? Strictly greater than 10? Is it over 10? And if it is no, it asks you to go back again to the beginning and input all the new set of inputs, and it recalculates and asks the question again. If it's a yes, then it goes on to output the results and then finish. Okay. So yeah, that's the basics of it. Okay. Yes. So pseudocode is less intensive, and if you're wondering, then pseudocode is spelled Pseudocode. Pseudocode. Yes, very simply, it is just basically going through and writing out what you want the program to do. So line by line. So if you were to have go through the program I just demonstrated, it would be, so you wouldn't have to write down start, but you'd say, right, on the first line, input num1. Okay, then you'd have input num2, then you do result equals num1 plus num2, or maybe even write in plain English. So say store the result of store num1 plus num2 in result. Then you'd say if the result is greater than 10, go back to instruction 1, it will go through again. If not, continue, output the result, and then finish the program. So basically, pseudocode is just writing out precisely what you want. So there are occasions when you might want either, and it's like pseudocode is very wordy, so it's better in my opinion for simpler programs, whereas flowcharts are much more visual and you can actually see how things will go, and they're a lot more interactive. And yeah, you can have pages and pages of flowcharts and still know roughly where you are. And little side note, if your flowchart goes over multiple pages, then you need, at the bottom of the page, so after the last instruction on the page, you put a little circle, and in the circle you put a letter, and that put a letter, and then on the next page, at the very top of the next page, you put another circle and put the same letter in that circle, and then continue the flow diagram from there. So imagine having a little wormhole in space, or a portal, and they both have the same value, and you go through one, you end up on the other page. Okay, that's a bit of a long-winded explanation there. So next we have different coding. Next up from flowcharts and pseudocode is actual programming languages, and there are two different types of programming, two different levels of programming language. There's high-level code, and then there's low-level code. High-level code is basically just code that is written in almost English. It's very easy to read, very easy for humans to understand. However, it hasn't got very much direct access to the hardware on the computer. It can do a lot, but it's limited in terms of how much access you have to the actual hardware. Low-level code is a lot more difficult to read. There are fewer instructions. However, but it has greater access to the hardware. You can directly access how the CPU functions and do stuff on a very basic level. The lowest code level is binary. However, that's a little bit difficult for humans to use. So we actually, the lowest level humans tend to use is assembly language, which has basically one command for every binary instruction. So it directly converts into machine code. So in order to work, high-level code has to be converted into low-level code, and that basically in order to do that, uses a translator, which is basically the computer taking the instructions you've given it in high level and looking at that, assessing that against a predefined table of commands, and saying, right, so this command means this set of machine code, this command means this set of machine code, etc., etc. So uses that reference table to be able to convert it, and then it runs the code. This is basically easier with a low-level language like assembly. This is faster and easier because there's fewer commands and they're basically directly translated into machine code. Okay, so then there are different types of programming language within that. So you have an assembler, which is basically used to program low-level code, and it gives direct, and as I said with assembly, it gives direct access to the hardware. It has very low level. It is difficult to code, however, because it has so few commands. You have to give it really long-winded ways of doing something really simple. So an example of an assembler language would be assembly. That's fairly confusing. Okay, next up is a compiler, which basically translates all the high-level code that you input into low-level code. before you run it. So then it creates an so a compiler translates all the high-level code that you've inputted into low-level object code before running. The object code is stored as a separate file, so either an it.exe file or maybe a .bat file or something else. You then run the object code independently of the source code, so that means it can actually generally be cross-platform and incredibly useful, and yeah, things like that. So because it's cross-platform, because the code and the object code can be run separately from the compiler. You do not need the compiler on a system in order to run the code. The code is also faster because you haven't got to continuously be translating it into machine code. And yeah, so it is also better because people cannot directly modify the code without having access to the source code. However, the initial compiling, so translating it from source code into machine code, is slow, so you need to set aside a little bit of time for that. And then once it has compiled, and if you come across an error, it can be a little bit difficult to try and find out where the error is and how to fix it. An example of a compiler language would be C++, which is generally used to create games, and actually most apps as well, so it's incredibly versatile. Finally, the final type of code is an interpreted language. So an interpreter converts high-level code into low-level code, like a compiler, but only when it runs it. And it converts it and runs it line by line. So it goes through the file and converts each line as it goes along into code, into machine code, then runs it. So it produces no object code, and that means that it does need to be translated every single time it's run. So an example of this would probably be Python. So of course, because it's being basically debugged as it's going along, and it's going through and finding when translating is going along, it is very easy to debug this type of code, and that can also result in a shorter development time. So if you look at some of the projects on my channel, some of the more complex looking projects only took me maybe a week, maybe a weekend or a week or so to do, because I'm doing it in Python, which is an interpreted language. It is also portable as long as the target system, so the computer that you're putting the software on has the interpreter that you need. So I can run any of my Python code on any computer as long as it has Python installed, which is fairly useful for Mac users because Macs come with Python installed. This can also be a drawback because you must have it on the system, and the interpreter actually takes up space on the memory in order for you to use it, so therefore it fills up space on the computer. The code also runs more slowly because it's having to be translated constantly as it goes along, and people can also really easily modify the source code because you have to have the source code on the computer in order for it to run. Okay, so when developing code, most people use something called most people use a integrated development environment, or IDE. I pronounce it IDE because it's easier to say. And basically they come with IDEs come with multiple features that make it easy to edit code. So it comes with a text editor, which is needed in order to actually edit the code, so that is a major thing to have. It comes with error diagnostics, which allow the computer and system to spot errors and make sure that the developer notices it before actually running it. It comes with a runtime environment, which basically is a safe environment for the developer to run the code and to see all the outcomes and everything. And then finally, then you also have a translator, as mentioned before, in order to convert the code into the high-level code into machine code. And then finally, it has auto documentation, which is included to keep track of things like variables and modules and comments. So modules are basically packets of reusable code that you can repeat over and over again if you need to, and comments are basically just there to help a programmer keep track of things and to tell other programmers and developers what different parts do. I'll cover variables in a bit. Okay, so next you have program sequencing. So program sequencing is the process of putting the code in the correct order. So the sequencer of a single program would basically just be from A to B to C. So this is an example of a basic program. So you have the start, and it goes to the first instruction, and the second one, and the third one, and the fourth, and then finishes. It's very simple. However, sometimes programmers need the code to make decisions, and that's where branching comes in, and that can create a very complex sequence. However, all sequences end with the finish. It always finishes at some point, and we'll cover if statements and things and branching later on. Selection is basically the process of the computer or the program choosing which path in its code to take based on a set of conditions. So this is so the events only happen when you want them to. So, So when a specific button is pressed, or the mouse goes over a certain area on the screen, or maybe even when the temperature in the room is a certain temperature, is a certain level. So iteration is a fancy way of saying repetition. So in programming, it means that a set of commands will be repeated over and over again. So in this example, it goes 1, 2, 3, 4, 5, and then 5 tells the fifth instruction tells the computer to go back to number 1, and then it will run it all again, and then go round. And this is an infinite loop, and we'll cover infinite loops in a little bit. And it'll continue iterating and repeating until a certain set of conditions are met. So best example I can think of is probably in games. So the main loop of the program that tells it to continuously update the graphics and variables and maybe your health bar or something will continue going until you tell it that you want to exit the game and quit. Okay, so a variable, let's go back to variables now. So a variable is a section of memory used to store a bit of data that will continuously change and be rewritten and be different from moment to moment. So this could be an example. This will probably be a clock, so it continuously counts up, or maybe a variable holding whether or not a button has been pressed. Okay. A constant is basically the opposite. It is a section of memory that is assigned to a particular type and amount of data. It will only be able to contain a specific piece of data. So an everyday example of a constant would probably be the speed of light. The speed of light remains constant even throughout the entire space, entire of a vacuum or something. For those of you who don't know, the speed of light in a vacuum is 299,792,458 meters per second. Yay, nerd. So in order to set a constant or a variable, they must be given a name in order to identify them by in the code, so the computer knows where to reference in the memory in order to get the value that's stored in the variable or constant. And it must also be given a value to hold. So whether that is a placeholder, like just the number 0 maybe, or the actual value, but it must be given something to hold. So it's also a good idea to remember naming conventions for variables. They must be descriptive, simple but descriptive. So maybe if you're holding, maybe if you've made an app and you need to create a variable to store the height of a window, it'll be advisable to maybe name it win height, the variable win height. So WIN, capital H, EIGHT, so no spaces or underscores or anything. And that method of doing things is actually called camel text. So you bunch all the names of all the different words in the description together, remove the spaces, and then make each new word, give each new word a capital letter, except for the first one, which has lowercase. That's fairly confusing, and it might come in handy, but but it might not. You never know. So we have touched on this previously, but there are different types of data. We covered this in database, I think it was, when talking about setting field properties and things like that in a flat file database or something. And so there are 5 different types of main types of data. And you have Boolean, which is whether something is true or false, or on or off, and it basically anything that can be represented by either a single 1 or a single 0, a single bit. You then have integers, which is any whole number. You also have real numbers, which is any number, whether that is a decimal or a whole, or a fraction or something else. Then you also have a character, which is a single byte of data that is usually ASCII, and it will contain a letter or a number or a symbol of some sort. And then finally you have a string, which is a collection of characters, and whether that is a collection of numbers, a collection of and it could be numbers, letters, capitals, lowercase, or symbols, anything. So integers would best be used for iterative counting, so that's going 1, 2, 3, 4, 5, so going up in ones every time, or going up in a set amount. But on the other hand, reals will be better for complex calculations, so things like fractions or continuous data such as height. Most people are not a precise centimetre in height. As I mentioned before, a Boolean would store whether something is on or off, or true or false or something. And then characters and strings would probably be used for, well, strings would, the most common use of strings would be names or passwords or something like that. So for example, Sam would be stored in a string. And then maybe characters would be stored for something that can be represented with only a single byte of data. So maybe your gender. So your gender could be represented as either M for male or F for female. Okay, so there are then different processes that you can carry out on numeric data. So you have the ordinary ones, so you have add, subtract, multiply and divide, and all of these can be carried out on the computer. So you need to remember the different symbols that you use for these things. So add as an ordinary add symbol, the subtract sign is the hyphen, so remember that. However, the multiply is the asterisk, which is the little star that you sometimes use for footnotes and things. You need to remember that it isn't X, because X is the letter X, obviously. So you have to use the star, and then divide you use the slash, the forward slash rather, not the backslash, the forward slash. Forward slash that'll look like that to you. There is also modulus, which in Python is represented by the percentage sign. However, you could just write the letters MOD in capital letters and it would work fine. And that basically, when you give it 2 numbers, it'll return the remainder after dividing the first number by the second number. So the example I've given here is dividing 14 by 3 would give you the remainder of 2. You then have the quotient, which I couldn't find, which I don't know the symbol of for Python. However, you can just use the letters div, and basically using quotient on two numbers will give you the number of times that the second number goes into the first one as a whole number. So basically, when you divide 14 by 3, you get 4. So you could probably represent that number by saying, because basic way to sum this up is that timesing 4 by 3 gives you 12, but then adding the result of the modulus of 14 and 3 gives you, to it gives you 14. So 14 divided by 3 is 4 remainder 2, so it can be split into modulus and quotient. Okay, so however, you're not always using just numeric data, you're also using Boolean data. And basically a computer can also manipulate and assess Boolean values using different symbols. So we touched on this earlier in this episode with when we were going over flowcharts, and you saw the greater than sign. Well, there are a multitude of different symbols and things to represent different inequalities and things, and for checking whether something is true or false. So a computer can assess if two inputs are equal, so using the equal sign, or in some programming languages a double equal sign. It can say if one is strictly greater than the other one, which is the usual greater than symbol. It can also say if it's strictly less than, using the less than symbol. It can also say whether something is not equal, not the two values are not equal, and those can either be represented by a greater than, a less than rather, strictly less than sign facing into a strictly greater than sign. However, the way I prefer to do it, which is the way they do it, they do it in Python, is to put an exclamation mark and then an equal sign. You also have greater than or equal to and less than or equal to, which is represented by the sign for either less than or equal, less than or greater than, followed by an equal sign. Okay, so these operators, well, these are called operators, and they're most usually used for using if statements or controlling loops. So if this statement is true with these operators, then do this bit of code. If not, do this code, or loop until this specific condition is true. Okay, you then have something called arrays, and the most simple array is a one-dimensional array. And a one-dimensional array is a list of values. So they usually a list or an array is used to store a list or set of related data, such as height, or in a very simple game you might use a list to reference. Use a list to hold the values and the attributes of a character. But the most important thing to remember about lists is that in most programming languages, the first item in a list or an array is not hasn't got. Oh, right. Let me backtrack a little bit. Okay, so each item in a list or an array or a set has a number, which is called an index number. The most important thing to remember is that the first item in a list or an array has not got the index 1. It has the index 0. You have to remember that. So yes. Moving on to errors, which I have made plenty of. And okay, so you have different types. There are two main types of errors, and those are logic errors and syntax errors. So a syntax error is basically when what you've coded or programmed goes against the rules set down in the memory for the program that for the language that you have used. So maybe not correctly typing in your not correctly using the operators and the conditions, maybe not using the correct symbols to represent different types of data, or maybe just trying to divide a number, divide a word by 100. And then you have logic errors, which are basically rules that, where you don't break the rules, and the error does not make itself apparent. However, the way that you have coded coded something has meant that the program doesn't work properly or produces an unexpected result. Both can cause crashes in the software. So the most common logic error, and actually this can also cause a syntax error, is probably trying to divide a number by 0. This is called a zero division error. I can't tell you the names of all the different errors because there are so many that can come up. But I'm sure there are lists out there of different error names. Some other common logic errors are things like creating a never-ending program that has an infinite loop, so with maybe conditions that will never be met, so maybe having an ordinary household computer in a room that is 100 degrees centigrade. That will most likely never happen. Another one is creating a stack overflow, which basically means that the memory fills up with data and causes the program to crash, and actually that can cause some fatal errors to your computer as well. It's the cause of it's the main use of a certain virus. I can't remember its name, but it's a virus that basically it goes into a system and it finds the largest file it can and then copies it over and over again to create something. It is also the main reason why the website crashsafari.com will crash your iPhone. It fills up your history with stuff and causes it to crash your phone because the memory fills up too quickly. Okay, so syntax errors, I haven't got any examples of syntax errors, but they are a lot easier to catch because IDEs and IDEs use the error diagnostics stuff to try and find syntax errors and warn the developer of a problem before they run it or compile it or do something that they shouldn't do. Logic errors because the logic error relies on you not doing something right, the computer cannot spot logic errors because it doesn't know what you want to do. Okay, final section, I promise, is testing programs. So to test a program for errors, you need to be able to test for, you must use a variety of data. Because all it takes is the wrong input in the wrong place to cause your program to crash and for the entire thing to go wrong. So test data should be a combination of valid data, so data that will be inputted on a everyday sort of usage, extremely valid extreme data, so data that could be entered in a normal situation but might possibly not. It's at the extreme end of whether or not it would cause an error or not. Invalid data, so data that should theoretically be rejected by the system and cause a crash or an error. Invalid extreme data, which is basically invalid data that is only just invalid, so data that could cause a crash but is on the verge of being okay. And then erroneous data, so data that should be rejected because it is completely the wrong type of data. So for example, entering a string where the computer is expecting a number. Okay, so when testing, it is very important to keep track of the results of your testing, so that you can then go back later and fix the errors that you've come across. So the easiest way is to create a table to record your stuff, the results in, and each column of the table should have the type of test you're carrying out, so whether that is a valid using valid whole numbers or invalid non-numeric data, the data that you're going to input, so whether that is the word cat or the number 124 or something, and then a final then a column for the reason why you're inputting the data, and then finally the expected result. What result are you expecting from this code running with this input? You can also then, it's also a good idea to record the actual result, so to either write a summary of what actually happened and compare that to what you expected, and then if there is a problem you can then go back and fix it and compare it to the result and previous results. Okay, so that brings us to the end of not only this chapter but also the end of the theory section of the computing course. This is the end of the series, so if you watched all the episodes, congratulations for hanging on this long. Do not forget to continue to go over the information I told you. Maybe watch this again, test yourself, go to teachict.com, I think that's what it's called, or there's even a computer science section on the BBC Bitesize website. I'll try and put links to those in the description. Also in the description you will find a link to a downloadable copy of the scripts from all the episodes this week. They're not word for word perfect to what I said in the actual episodes, because these were only rough notes for me to follow really. However, they you might want them because they all come because at the top of each section I have put the syllabus in question form, so that could be useful for you testing yourself or going over it, or and if you're maybe asking somebody to test you who doesn't necessarily know a lot about computer science, they can look at the scripts and go they're in the order. Most of the scripts are in order of the questions. So first one, what is a computer system? The first sentence of the first script is a computer system is a collection of electronic components that work together to receive and process inputs to create a useful output. Okay, so it's things like that that you might find useful, so check that out in the description. So yes, if you found this video or even this series helpful or useful, or maybe or if you're that kind of person, interesting or enjoyable, make sure that you like and subscribe. If you know somebody else who might find this helpful or useful, or especially as they're doing this exam on Wednesday, make sure you share it with them using either Facebook, Twitter, your social media. Send them a text with the link in anything. And then well, again, other than that, there's not much else to say other than thank you very much for watching.